Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to General class. This episode is Subelement G4, Question Pool D, and I'm your host, Ron Call, KE7CR. This question group deals with speech processors, S-meters, and sideband operation near band edges. So let's get started. The first question asks, what is the purpose of a speech processor in a transceiver? Well, a speech processor is supposed to just focus on the frequencies of the human voice. Normally, a lot of microphones are designed to give a kind of a wide, broad range, so you can include music, other notes, lower frequency than the voice and higher frequency than the voice. But a speech processor is supposed to cut that out, really pack all of your energy into just the bandwidth of the human voice. So the effect that it has is to increase the apparent loudness of transmitted voice signals. That's the answer. The next question asks, how does a speech processor affect a single sideband phone signal? Well, it increases the average power. Again, because you're taking all of the energy and packing it into a smaller bandwidth. So it increases the average power. The next question asks, what is the effect of an incorrectly adjusted speech processor? If it's focusing on just the lower frequencies of the voice or the higher frequencies, you're going to get distorted speech. That's one of the options. Another option is excess intermodulation products, which again, as you have different frequencies interact, you can get mixing of frequencies to produce even more frequencies. So that's a problem if the speech processor is not adjusted correctly. Or you could get excessive background noise. If the microphone and the speech processor are picking up extra noise from the background and not filtering that out, you're going to get that as well. So the answer for this question is all of these choices are correct. Next question says, what does an S-meter measure? S-meters stand for signal strength meters. So I've got a picture here of an S-meter. Some of them are analog meters, others are digital but simulating an analog needle, like this one. Or you can have an LED S-meter. This is a digital S-meter. But they all measure received signal strength. An S-meter picks up the power from the receiver and uses that to indicate the received signal strength. So that's the answer to that question. The next question asks, how does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S-meter? So you need to understand that S-meters are used to represent signal strengths in dB or decibels, and that they go in S units. So you'll see it say S1, S2, S3, S4, and each S unit is equal to 6 dB. Now you need to remember that double the power level is 3 dB. So 6 dB is going to be 4 times the power level. Now once you get to S9, that's a very loud signal. Over that, they just say 10 times over, 20 over. It goes in increments of 10 over S9. So the way to read this is if you're 20 dB over S9, starting with S9, if you went 3 dB over that, that would be twice the amount of power. 6 dB, 4 times the power. So you can say, well, 3, 6, 9, 12, 15, 18, you're getting close to 20. So 20 would be partway between 6 and 7 S units. It's about 6 2/3 S units. So you could think of it as going from 3 to 6 to 9, 12. That's twice the power, 4 times. Double that again to 8 times, then 16, 32, 64, and then not quite 7, which would be 128. So you know it's between 64 and 128. The answer choices are 10 times less powerful, 20 times less powerful, 20 times more powerful, or 100 times more powerful. The best answer is it is 100 times more powerful. If you calculate it on a calculator, if you take 2 to the 6.67th exponent, it's 101.8. So that's our best answer, is 20 dB over S9 is about 100 times more powerful. Next question, how much change in signal strength is typically represented by 1 S unit? That we already mentioned is 6 dB. Next question, how much must the power output of a transmitter be raised to change the S-meter reading on a distant receiver from S8 to S9? So if you think S8 to S9, it's 1 S unit, that's equal to 6 dB. So remember, 3 dB is twice the power, 6 dB would be 4 times the power. So that's the answer, approximately 4 times. Next question. What frequency range is occupied by a 3 kHz lower sideband signal when the displayed carrier frequency is set to 7.178 MHz? You need to remember a sideband signal has a bandwidth of about 3 kHz. The frequency displayed on the transceiver is typically the carrier frequency. And for lower sideband, it's 3 kHz below that carrier frequency, up to the carrier frequency. So if you take 7.178 minus 3 kHz, it would be 7.175 megahertz up to the carrier frequency, which is 7.178. So that's the answer. Now, if it's upper sideband, it's going to be the carrier frequency plus 3 kHz above that, which is the next question. What frequency range is occupied by a 3 kHz upper sideband signal with the displayed carrier frequency set to 14.347 megahertz? Well, it's going to be 14.347 plus 3, which is 14.350. So that's the answer there. The next question asks, how close to the lower edge of a band's phone segment should your displayed carrier frequency be when using a 3 kHz wide lower sideband? It's at the carrier frequency and the signal extends to 3 kHz below that, so you want to make sure you're at least 3 kHz above the edge of the band segment. And the last question, how close to the upper edge of a band's phone segment should your displayed carrier frequency be when using 3 kHz wide upper sideband? Again, it would be at least 3 kHz below the edge of the band. All right, that's it for this question group. Thanks for being here, and we'll see you for the next group.